Good day, I'm Norman Wapperger. In this very important video, we're going to summarize the case against this definition of a real number. The idea that a real number is an equivalence class of Cauchy sequences of rationals. Introduced by George Cantor, this idea is probably the most comfortable with most pure mathematicians. It's the one that they think about intuitively and immediately when somebody asks them what is a real number. We're going to look more carefully at the various terms involved, and we're going to summarize the case for the prosecution against it. Okay, so I claim that this definition doesn't really work. The notion of real number is logically seriously flawed, and ultimately I'm going to try to convince you that there's a more beautiful, better mathematics out there once we get past this obstacle of believing in these things which don't really exist. Okay, there's a lot of repetition, memorization, and blind adherence here involved. And it's going to be challenging for many of you because you've been indoctrinated to believe that real numbers exist. And it's going to be a hurdle for you to let go of this idea. So try to be objective. Let's have a look at the difficulties fair and squarely. We're going to have to venture a little bit into the never-never land of infinite sets when we talk about, what equivalence classes are and their relation to this definition as well. Okay, we ready to go? Let's proceed. The first problem that we're going to look at is the ambiguity with the meaning of the term infinite sequence of rationals. So it's important to understand that it's not self-evident what an infinite sequence is. This is a term that has to be defined and defined very clearly in mathematics. And it's unfortunately very difficult to do this, and so most of the time people just pretend that there is an adequate definition out there and they're not responsible for laying it out. But here is already a source of a lot of the errors in that we're not clear enough about what the words mean. So remember that in mathematics, the keywords all have to have precise definitions on which we can all agree. Okay, so what are some of the issues? Well, certain very important issue is this difference between choice and algorithm that we have emphasized quite a few times. Okay. So if you're given an infinite sequence, say S, whose terms are S1, S2, S3, and let's suppose that they're all rational numbers, so at least the actual individual elements are okay. Then there's at least two possible ways of interpreting what we mean when we say, oh, let's consider this sequence. One thing that we possibly could mean is that we're thinking about this sequence as being given by an infinite choice operation. In other words, we're thinking about the sequence as being just a string of numbers that somebody or someone or some machine has produced and laid out on a tape for us, with this tape going on infinitely. In other words, there's no necessary rhyme or reason to the entries. There doesn't have to be a pattern. There doesn't have to be an algorithm or a procedure or a law or a rule that generates the sequence. In our minds, we can imagine a person, say, who happens to be able to live forever, just making up rational numbers, one at a time, independently, perhaps sort of randomly, whatever that means, to infinity. This tape just keeps on going and keeps on going and keeps on going past any physical barrier that you can possibly imagine, so essentially beyond the bounds of the universe. Just keeps on going with more and more rational numbers. That's one way of thinking about what it means when I say, oh, let's consider this sequence. Another quite different way of thinking about what those words mean is that we're talking about an algorithm. That we're presenting somebody with a rule, or an algorithm, or a procedure, or a law that generates the terms of the sequence. For example, maybe the formula Sn equals n squared plus 3 over n to the fourth plus 4. This is a particularly pleasant kind of thing that we've already identified as a suitable, solid kind of mathematical object. so-called rational polynumber on sequence. But the modern mathematician is happy to consider all kinds of other variants. Or perhaps we could have a recursive formula. For example, this one here, S1 is 5, and maybe Sn plus 1 is Sn squared minus 4 over Sn plus 2. That would be another way of generating a sequence. Or maybe we have some kind of computer program kind of thing that gives us a bunch of instructions written in some programming language that will output the terms Sn one at a time. So there's all kinds of possible variants to this, but the basic idea is that we have to have a finite way of writing down the instructions for generating the sequence. So in this case, it's the instructions themselves that sort of capture the sequence. The actual terms of the sequence are, in some sense, sort of secondary. It's the instructions themselves which are the key part of the sequence. Okay, so very important to understand that there's a huge gap, a gulf between these two ways of thinking about what a sequence is. And various questions and issues will be dealt quite differently depending on whether you take this position or this position. And it's perhaps worth pointing out that these are not the only two positions that one could adopt. Okay, these are sort of the most logical two, the ones that are usually found. But it might very well be that someone has some combination of positions that they're going to think, when they say infinite sequence, they're imagining that there might be some algorithm, say, that generates all the odd terms of the sequence, and all the even ones are given by some infinite choice. Okay, maybe it's possible to imagine that kind of thing. So the point is that unless we clarify what the word sequence, or especially infinite sequence, means, then it's not clear whether we're talking about this kind of object or this kind of object or something in between, or maybe something even a little bit different. Okay, so let's have a look at the various problems that come about with this idea of sequence, depending on which of these two options we are imagining our definition encompasses. So, problems with the choice approach to infinite sequences first. Okay, so if your position is that an infinite sequence means a bunch of rational numbers which have been just chosen randomly and independently with no necessary rhyme or reason to them, then you have to deal with the following problems. First of all, very key point, there are no examples. You are talking about a mathematical object for which you can give no concrete example. Because all the Cauchy sequences of rationals that actually come up in practice in mathematics, Cauchy sequences for pi or e or root 2 or log 13 or sine of 5 or some integral or some infinite sum or anything else that you're probably likely to be able to cook up, all of these are given essentially by formulas or algorithms. There are no known examples of choice approaches to infinite sequences that are complete. A true example would require an infinite amount of time, memory, and information to write down. To exhibit it would require an infinite amount of resources. The universe is too small to contain such an object. There's just not enough room to string an infinite number of rational numbers in a row somewhere. So the best that we can do is to imagine an infinite tape and then to say a few initial ones and then put 3 dots at some point and then pretend that this is sort of adequately representing this thing that we're imagining. Okay, it's a far cry from exhibiting 1 or 3 or 300 and then some dots to actually specifying the whole thing. Secondly, related to this, any operations with such sequences must involve an infinite amount of time and memory. In other words, they're completely impossible. If we're imagining two sequences given by choice, and we're then telling someone, well, now let's add these sequences. And we say something like, to add these sequences, we just add them component-wise. So we add the two first ones, and then we add the two second ones, and then we add the two third ones, and so on. Easy enough to say that. But what we're really asking the person to do is to do an infinite number of steps. You cannot actually make the calculation until you've done an infinite number of steps. It's completely fictitious, absurd kind of scenario. It's impossible. It's completely impossible. So this approach is very much in some kind of fantasy fairy tale world land, divorced from any real connection with the real world in which we're living. Why do we do it? Because it fulfills certain wishful dreamings that we have. That's the reason. It's not because it makes sense. Okay, but on the other hand, if we have a very algorithmic point of view to what a sequence is, there are still serious problems, serious logical problems. For example, the whole discussion requires a prior definition and theory of algorithms. We have to have already ventured into computer science land and learned a lot about programming, about algorithms, about machines and so on, and brought those back into mathematics and made them mathematically precise before we can talk about sequences as given by algorithms. Secondly, it requires choices, reprogramming languages, machines, types of programs, and so on. There are all kinds of choices that we make when we're talking about computational issues in terms of machines and languages and compilers and so on. And we have to discuss the relative merits of these different approaches and whether ultimately they give us equivalent theories or not. Again, it's a very subtle and delicate issue that unless we know a lot of computer science, we're likely to be uncomfortable with. And the reality is that most mathematicians, if they're going to go in this direction, probably don't have the requisite underlying computer science background in order to be able to honestly lay things out to make things work. Then there's a very difficult obstacle, okay? The equality of algorithms. Okay? So if you're going to believe in sequences as being generated by algorithms, well, deciding whether two algorithms gives you the same output or not is essentially an intractable problem in general. Okay, it's sort of well known that this is almost impossible. Well, probably it is impossible. So you're not in a position to be able to say that we can for sure determine whether given algorithm 1 and given algorithm 2, they're actually going to generate the same sequence. So related to that, there's no canonical forms. There's no best or simplest form for an algorithm that allows us to quickly compare different algorithms. And then there are issues going back to Church and Turing, founders of computational mathematics. And these issues are, again, having to do with whether different kinds of computability are actually the same. Is there just one notion of computability? When we say it's sort of a computable sequence, we have this idea that yes, it's generated by a machine, but is there really just one notion? Maybe there's several different types of notions of what a computable sequence really is, depending on the types of algorithms that we might allow. So there's serious technical issues here that, again, one has to deal with before we are confident that an algorithmic approach to infinite sequences works. But even if you've mastered these ones here, this number 3 is a central problem that is not going to go away and renders this approach a very, very problematic logically. The second major problem is that the Cauchy requirement itself is inherently ambiguous. The ambiguity takes different forms depending on what approach to sequences we have. If we have a choice kind of approach, then verifying a sequence is Cauchy requires an infinite amount of work. This is the kind of situation that we talked about with Collat's conjecture kind of example. Okay? But for a general choice sequence, which is given not just by a complicated computer program, but perhaps just by some essentially random choice of rational numbers, verifying that for all epsilon greater than 0, there is an n, a rational number, such that little n and m bigger than capital N implies that the difference Sn minus Sm is less than epsilon in absolute value. That requires, in general, an infinite amount of work, because you have to check the existence of this n for an infinite amount of epsilons. And for your general, run-of-the-mill, typical choice sequence, there's not going to be any way of avoiding that infinite amount of work. So although you can phrase the definition and say, oh, it's, the limit exists if this and this happens, in fact, you're actually requiring an infinite amount of work to check whether this condition is actually satisfied or not. And that's, in my view, not a proper definition. On the other hand, if you have an algorithmic approach to sequences, the problem manifests itself in quite a different way. In that case, the definition is unclear about whether knowledge that a given sequence is Cauchy comes with an algorithm to determine n from epsilon. Let me explain what I mean here. So suppose that we're working in the algorithmic world, that all the sequences that we're thinking about come from some kind of algorithm. Okay, so I give you an algorithm. Here's an algorithm, and it generates some sequence. And then I say, okay, this is a Cauchy sequence. It has this property. Now, what does that mean? When I say that there, for all epsilon, there exists this n, what does it mean? One interpretation is that there's an algorithm. There's a separate algorithm, different from the one that I've shown you, that generates the sequence. There's another algorithm that generates the n's from the epsilons. So this second algorithm, I input an epsilon in it, let it run, and it will pop out the n that's required for this definition to work for that given epsilon. That would be one interpretation of what it means when we say, for all epsilon, there is. We're asserting the existence of something. If you're working in an algorithmic world, you could interpret that to mean there's an algorithm to do it. On the other hand, it might mean, if you're a choice mathematician, you probably think that it should mean, oh no, there is some relationship here, but it may require an infinite amount of work to establish the relationship between these epsilons and n's. So even the meaning of this statement is not really very clear. Okay, so it's not the case that such a thing necessarily exists. So even for this Collatz extended harmonic sequence, which we saw was a very pleasant, algorithmically generated sequence, we saw that in fact there wasn't an algorithm, or at least we don't know of one, and we don't know of the existence of one, that gives us the n's for the epsilons. Okay. So just because we have an algorithmically generated sequence does not mean that we necessarily have an algorithmic way of computing n's from epsilon. So there's this element of infinity that will creep in even if you're a bona fide computer kind of person and you just want to restrict to finite things. Nevertheless, this condition of this Cauchy requirement is intrinsically infinite. You're going to have a hard time escaping that. Let me rephrase that difficulty perhaps in a slightly different way. So here's another way of saying it, that deciding whether a given algorithmically generated infinite sequence, say this one here, perhaps given by some algorithm that might look like this, given n for k from 1 to n do, and then do a number of things, and then eventually output Sn. That's a little program that generates, say, that sequence. It's a very specific program. We're imagining it very concrete, finite. We can run that thing, fine. But to decide whether this sequence that we've generated this way is or is not Cauchy is almost surely impossible. So for such a sequence, suppose we ask, okay, does this sequence, say, have a limit? Or is this a Cauchy sequence or not? These are questions that we cannot in general do. Right? So if we could do these kinds of things, then we could solve a lot of famous problems. So this criterion of, a sequence is Cauchy or not, it really is asking us to check an infinite number of things. That's why it's impossible for us to do it in general. Okay? It's not a finite kind of question like, is this number bigger than this number? Or is this number times this number equal to this number? It's not like that. It has an infinite aspect built into it, making it sort of logically very problematic. The next problem has to do with the other sort of major term which is involved in the definition, the idea of an equivalence class. So the meaning of equivalence class is also ambiguous. Okay, so to understand this really, we would have to venture into the dream world of Cantor's infinite set theory, which claims, amongst other things, that there are things such as infinite sets, classes, paradoxes, no, sorry, not paradoxes, there are no paradoxes, equivalence relations, equivalence classes, hierarchies of infinities, hierarchies of angels, no, sorry, not hierarchies of angels, inaccessible cardinals, yes, there's inaccessible cardinals, there's lots of choice, freedom of thought, there are axioms, there's Zermelo and Frenkel that we pay homage to, truth, beauty, and many other beautiful, lovely, incredibly interesting things. Sure. As long as you sort of, are happy to stay in a reclining position and not sort of wake up and, actually look around and see what's actually the case. Okay. This is a big, elaborate dream world, not supported by proper definitions or clear arguments. I'm going to eventually venture into this infinite world, this infinite dream world of Cantor. I'm going to talk about infinite sets. You already know that I don't believe in them. Neither should you. Okay? But there are a lot of auxiliary concepts which don't work properly when you go from finite sets, which are perfectly fine and interesting, in fact very interesting, to infinite sets as they are currently laid out. So the equivalence classes story is part of this make-believe world, and one should be highly suspicious of it for that reason. All right, so without going into the whole details of the difficulties with infinite set theory, let's at least summarize the aspects of it that are sort of relevant for this discussion. Okay, so the first important idea is the idea of an equivalence relation. I can at least show you what it's like here in the case of these infinite sequences of rationals we're talking about. So if we have two Cauchy sequences of rationals, okay, when I say, we have two Cauchy sequences of rationals, it's all in quotes, right? Because this is all a little bit of a fantasy as far as I'm concerned, but let's play along. So we're imagining sequence S and sequence S prime. And again, our imaginings are going to be dependent on whether we have a choice point of view or an algorithmic point of view. So what we're actually imagining is potentially quite different from what our friend is imagining. So we're imagining something. Okay, here is the definition that we say that S is equivalent to S prime. These two sequences are equivalent. We're making this definition. Precisely when the limit, as n approaches infinity, of the difference Sn minus Sn prime equals 0. If we take the differences between these two, and look at those differences, if those differences, which are rational numbers, go to 0, if their limit is 0, then we say that the sequences are equivalent. So this is called an equivalence relation in set theory. And that means that it has certain basic properties, three basic properties. First of all, it's sort of idempotent, so any sequence is equivalent to itself. Yes, that's kind of clear. And the second that is that it's symmetric. So if S is equivalent to S prime, then S prime is equivalent to S. That's also pretty clear. And the third, which is usually the trickiest one to verify, is the so-called transitive property, which says that if you have three sequences, say S, S prime, and S double prime, if you know that S is equivalent to S prime, and you know that S prime is equivalent to S double prime, then it is the case that S is equivalent to S double prime. So if this property holds, we say it's transitive. If all three properties hold, then this is called an equivalence relation. Okay, so in our situation, this is an equivalence relation. But a natural question is, how do you tell if two Cauchy sequences are equivalent? Again, the answer depends very much on whether you have a choice point of view or whether you have an algorithmic point of view. If you have a choice point of view, you just imagine having a new sequence, which is the differences, and now you have this new sequence of rational numbers, and it's just a question of deciding whether its limit is 0 or not. And for that, all you need to do is just observe the whole sequence to infinity. That's all. A few billion years later, still no problem, but we're just checking to see that the limit's 0. So past the end of time, yes, finally, whatever that means, we're able to see the whole sequence, whatever that means, and to verify that, yes, the limit is 0. Okay, that's in my view, sort of completely silly kind of a notion, but okay. So then there's a more sensible algorithmic approach. Okay, you have two algorithms, one for this one and one for this one. What does it mean for the two sequences to be equivalent? Well, it means that you generate this difference sequence, and then you have to tell whether its limit is 0 or not. But we've seen that this is essentially impossible, because now you're no longer allowed to do this infinite amount of work that the choice people are imagining themselves able to do. Right? Somebody believes in choice, says, "Oh, just go and do an infinite amount of work, no problem. We believe in that." Okay? But if you're a computer scientist, you don't believe in being able to do an infinite amount of work. You can't just wave your hand and say, "Oh, now we do an infinite amount of work." No. You have to have a program that will do something for you. And in general, you cannot do this. This is impossible. As we've seen with this Collatz sequence that we talked about, right? Deciding whether the Collatz sequence is equivalent to the sequence 0, 0, 0. These are two sequences which are completely given by algorithms. This one a very simple algorithm. This one not too hard. Deciding whether equivalent is essentially equivalent to solving this famous Collatz conjecture. So you can see that this condition, saying, oh, this is equivalent to this if this condition is satisfied, you very well can say that, but even in practice, it's either ridiculous or impossible. Of course, you don't see this in analysis courses because they don't present these kinds of typical examples. They consider only very specialized examples that have been cherry-picked, baby examples, where everything works out and you have a nice little difference and you end up with a sequence, 1 over n squared. And oh yes, 1 over n squared goes to 0, so yes, everything is hunky-dory. All right, so carrying on with problem 3, the essential problems having to do with this idea of equivalence classes. The natural question now is, what is an equivalence class? I've mentioned to you what an equivalence relation is, or at least told you about the equivalence relation that we're interested in between two sequences being essentially equivalent. What's an equivalence class? Well, the idea is that if you have some set and you have some relation, and it's an equivalence relation satisfying the 3 properties that I told you about, then you're allowed to, according to standard set theory, form equivalence classes. And what you do is you group all the things which are equivalent to each other into one big group. Okay? So if you put S in here, and if S prime happens to be equivalent to S, you have to put S prime in the same group. And if S double prime is also equivalent to S, and so therefore to S prime, you put it in as well. And if you have another sequence, say T, which is not equivalent to S, so therefore it will be not equivalent to S prime and not equivalent to S double prime, then you don't put it in here. So in here go all the things which are equivalent to S. And this whole thing is called an equivalence class. Why don't we call it an equivalence set? Well, that's a very instructive question. Okay? The reason is because in other applications of this sort of theory, we want to group things together like this, but because of the various paradoxes in set theory that are sort of floating around the boundaries of the subject, people realize that a lot of these big conglomerations that they would like to form, and conglomeration is another word, we might say grouping or collection or menagerie, there's all kinds of words we could use. But they realize that these things are too big in the sense that they're likely to be paradoxical if we view them as sets. So they adopt this sort of game where you call them a class instead of a set, hoping thereby to avoid any potential problems with sets which are too big. That's the reason for this terminology, and that's what it means in this case. So the upshot is that for the standard definition, a real number alpha is the equivalence class of a Cauchy sequence of rationals. For example, here's what a typical real number looks like. It's a big class, which I'll still denote with brackets. And here is one Cauchy sequence of rationals. And here's another one. And this one is supposed to be equivalent to this one. And here's a third one, which is also equivalent to these two. But of course, there's more than just these three, because we can modify a given sequence in lots of ways and still get equivalent sequences. In particular, you can modify any one or initial segment of such a sequence and it stays equivalent. In other words, if I take this sequence here and I say I replace that 1/3 by 349 over 73, then that will be a new sequence which is still equivalent to the former one. So it's also going to be somewhere in this list. So you can imagine the complexity here, that any sequence in this ostensible list has the property that if you pick randomly any finite number of entries and change them any way you like to any other rational numbers, that new sequence that you get will also be in the list somewhere. That's not the only way you can generate new elements in this equivalence class, for example. What you can do is you can take this sequence here and then you can add to all the terms some new sequence whose elements go to 0. For example, I could add the sequence 1 over n to this one, or maybe 1 over n squared, or maybe some much more complicated sequence. As long as it goes to 0, then by adding it term by term to this sequence here, I'm going to be assured of getting an equivalent sequence, which means it's also going to be in here. So the long and short of it is that these little 3 dots you see here are representing all the other sequences which are in this equivalence class. This 3 little dots is a very modest little placekeeper, because it actually stands for not just quadrillions, not just an infinite number, but a so-called uncountably infinite number of other additional sequences which are in this equivalence class. And so that's what a real number is. There, ladies and gentlemen, is a real number, according to the definition of Cantor. And it's not a very good complete picture, because none of these things are prescribed. This is very much a choice point of view, and this is also highly dubious. Doesn't it look like a beautiful natural thing to be doing arithmetic with? Right. On this, the foundation of calculus and analysis is built, according to the modern pure mathematician. It's a very sad story. It is a very sad story, I'm afraid. And unfortunately, it impacts on young people especially, because you are being taught this stuff which doesn't work. It's almost patently ridiculous. And it leads you to this fairy tale, rosy view of mathematics, which is actually quite divorced from the true beauty of mathematics, which is really out there, which you could actually touch and see and write down and admire. Very unfortunate. So I gave you a choice view of a real number. I probably should give you an algorithmic view as well. So what does a real number look like if you take the same definition, but you adopt an algorithmic approach to sequences? Well, it looks like this. You still have some brackets. There's an infinite number of stuff in here. And each of these things is a program, or an algorithm, or a formula, or a procedure. For example, here this might be something, a program like this. Given n, set this equal to this, do all these various things, output Sn. Here's another one, which is more like a function. Sn equals this. If n is congruent to 3 mod 8, it's equal to this. If n is congruent to 5 mod 8, etc., etc. Or it might be a set of instructions that doesn't look at all like a computer program. Maybe it's a set of instructions that says go to Wolfram Alpha. Input n, find prime factors. Maybe somewhere you have to go and consult your neighbor and ask your neighbor for some input. Who knows? Okay, depends on what you allow for a kind of algorithm. So anyway, we imagine all these different algorithms, and supposedly they're all equivalent to each other, but equivalence at the level of algorithms is almost impossible to check. So this is just as much a fantasy kind of object as the other one is, or almost as much. It's more sensible, but it's still pretty far out there. It's still far removed from actual reality. To further cement this position, I want to present to you a theorem which you may have already seen in my famous Math Problems 19 lecture, right, which talks a lot about some related issues. We're also talking about this problem of describing the continuum and these various unfortunate attempts that we currently have to setting up the real numbers. So my theorem is, and I think it should be a really famous theorem, I'm hoping you spread the word, that all real numbers are the same. Okay, and it's the proof is by inspection. So here's one real number, it's called alpha, and here are the various strips, endless tapes on which these sequences are written. So we're having a choice point of view here. So here's one sequence in the equivalence class, there's another in the equivalence class, there's another in the equivalence class. You might think, oh, this looks like it's pi. Look, there's 3, 3.1, 3.14. This is the kind of sequence that I see in my analysis texts. They look a lot more like this than like these. Yes, they do, because they're trying to convince you about something that's much more complicated than they would like you to think. Okay, that's one equivalence class determining a real number alpha. And here's another equivalence class determining a completely different number, a beta. Who knows, maybe it's root 2, because it starts 1, 1.4, 1.41, and so on. But there's nothing in these three dots to let you conclude that the sequence carries on like this. It might do wildly different things. Okay, these don't look very much the same, do they? But that's because in these three dots, which are in the rest of these equivalence classes, there are more sequences. And the reality is that a sequence that starts like this is also found in this equivalence class. And a sequence which starts like this is also found in this equivalence class. And the reason is because, as I've said before, you can take any finite initial portion of a Cauchy sequence, change it arbitrarily as you will, and you're going to get an equivalent sequence. So all these equivalence classes, representing all different real numbers, they all look exactly the same if you just look at the first trillion entries of each of the sequences inside. If you just restrict yourself to only looking at the first trillion entries of all the sequences, then all of the real numbers look exactly the same. And well, what if you replace trillion with trillion to the trillion to the trillion? If you look at all the first trillion to the trillion to the trillion elements of these sequences, they all look exactly the same. And since we're only capable of looking at a finite amount of stuff, clearly, just by inspection, we can see that these two real numbers are the same. In fact, any two real numbers are the same. QED. I think this is going to be a remarkable simplification for many math students, right? It'd be great now that we have all real numbers are essentially the same. How much simpler can mathematics really be? The fourth problem I want to talk about is this one, connecting with applications and infinite decimals. How do you convert an equivalence class of Cauchy sequences to an infinite decimal? Whether you're thinking about a real number as an equivalence class of choice sequences, or you're thinking of it as an equivalence class of algorithmically generated sequences, how do you go about taking your equivalence class and converting it into a decimal number? Or equivalently, how do you take an infinite decimal and convert it to one of your things? This is kind of necessary to connect with what the applied mathematicians and the physicists, engineers, etc. are doing out there. This is how we would like to actually computationally work with real numbers. So natural question is, how do you go from one to the other? Well, let's say you figure out a way of doing this. So now my question is, well, then what happens to the difficulties with arithmetic with infinite decimals? Remember when we were talking about infinite decimals and the problems with them, we had very concrete problems having to do with being able to do arithmetic with them. So my question for you is, what happens if we convert these problems into your situation? If I have two infinite decimal real numbers and I don't know how to add them because of some problem, say with some repeating nines appearing when I'm trying to add them, and I have a problem of carry and I don't know what to do, can I just convert both of them into your equivalence classes of Cauchy sequences, make the computation of arithmetic in that framework, and then convert back again? Can I do that? Can I then circumvent the actual problems that I had? Problem 5. Show us the arithmetic. Convince us that you actually can do arithmetic with these equivalence classes of Cauchy sequences of rationals. So challenge 1. Express the three most common irrational numbers, pi, e, and root 2, as equivalence classes of Cauchy sequences of rationals. Let's have a look what they actually look like, these equivalence classes of Cauchy sequences, when we actually apply the idea to the simplest irrational numbers. Okay, the ones that everyone uses for examples. How does all this philosophical theory actually implement itself in concrete situation? This is a litmus test for separating talking with actual real mathematics. Okay? Ask for examples. Ask to see an exact example laid out properly, clearly, and completely. If they can do it, you're likely to be convinced, or at least you're going to be moving in that direction. If they can't and just want to stay at the level of chat, talk, philosophize, jargon, then you should be skeptical. So, if you manage to be able to do this, here's challenge number 2. I want you to compute using the above. So using the arithmetic of equivalence classes of Cauchy sequences of rationals that you've developed. Please tell us what the answers to these 3 questions are. I'm interested in what is pi plus e plus root 2. I want to make a computation telling us what that is. And I'm interested in what is pi times e times root 2. And a little bit more challenging, what is pi to the e divided by root 2? So I want explicit answers to these 3 to demonstrate that yes, we can actually do arithmetic with these real numbers. Of course, it's a bit of a rhetorical question because we all know that you're not going to be able to do it, don't we? Is there anybody in even a little bit of doubt about that? We all know that if you ask a pure mathematician to evaluate pi plus e plus root 2, they're going to think for a while and then they're going to tell you, oh, it's just pi plus e plus root 2. They're going to repeat back the question to you. Well, if that's how you do arithmetic with real numbers, then you should be very happy if you're a student, because then you can just solve questions involving computation by just repeating the question back as an answer. The final issue that I want to tell you about is problems with relating rational numbers inside the real numbers. So the question is, what happens to the rational numbers? We have a very beautiful arithmetic with rational numbers. Very rich structure, beautiful number theory involved, classically very important, a fundamental tool for people in the practical real world. What's going to happen if we start to think about the rational numbers as being contained inside these new real numbers? Well, contrary to what you probably have learned, there are very serious consequences for this in terms of contamination of the arithmetic of Q with the arithmetic of R. The vagueness and the waffliness and basically the inability to make concrete computations that I've hinted at in my last problem in R end up affecting Q as well. Because the rules of deciding when two things are the same are no longer as stringent as they are in Q. Let me try to illustrate that with an example. So here is 2/3, a very nice rational number. And we know that 2/3 is also the same as 4/6. It's also the same as -4 over -6 and many other ones. But there's a very concrete way of telling whether two rational numbers are the same. When we think of 2/3 as a real number, suddenly the story changes completely. The nature of this rational number is completely transformed into something that's beautiful like a gem, into something that's like a pile of mush. Here's the pile of mush. Here's the beautiful rational number. Here's the pile of mush. Well, actually just the part of the pile of mush. There's much more. There will be, amongst the countably infinite strips of paper that represent the equivalence class of 2/3, there will be inside there the distinguished strip, which is just 2/3, 2/3, 2/3, 2/3, and so on to infinity. But unfortunately, there's nothing to mark this thing as distinguished. It's just one of trillions or quadrillions of various crazy-looking sequences, most of them that look more like this. So, in fact, of course, as we've just seen from our theorem, if you actually look at the finite initial sequences of this one here, it looks just like any other one. The point is that once you try to start doing arithmetic with rational numbers in the context of real numbers, then the anything kind of goes rules that govern real numbers will necessarily also apply to rational numbers. For real numbers, there are no canonical forms for anything. There's never any way of deciding that one particular algorithm is preferable to another, or that one particular expression is preferable to another. There's just this mass of essentially, sort of uniform descriptions of things. So, for example, we saw that this philosophy of doing arithmetic by repeating the question back as an answer, which is basically the only way you can actually really exhibit irrational number arithmetic. If you apply that to rational number arithmetic, you get a complete diminishing of the natural arithmetic that students learn. So that 1/2 plus 1/3, while though it may equal 5/6, 5/6 is just one of many possible ways of thinking about things. But this 1/2 plus 1/3 is also a legitimate possible approach to what it is. I mean, if pi plus e is allowed to be pi plus e, then why should not 1/2 plus 1/3 be allowed to be 1/2 plus 1/3? And you can see this also more clearly from the algorithmic point of view. If you have an algorithm to generate this sequence, well, then you very well could have an algorithm that basically computes this, or computes 5/6 directly. They're all going to be just examples of algorithms in this big equivalence class. And finally, for example, suppose that you have some calculation like sum of n equals 0 to 10 of 1 over n squared. Well, in ordinary arithmetic, you would be obliged to actually work this out. But if you're working over the real numbers, you can claim that, well, all what you really need to do is calculate it like this. So here's another example of that. If we have, for example, the sum n equals 0 to infinity of, say, 1 over n cubed, say, times n factorial. Right? If I ask someone who's doing real number arithmetic, what is the value of this infinite sum? Well, with real number arithmetic, this kind of thing is just represented by the formula itself. There's in general no more efficient way of describing what the number is than just to write it down again. So the calculation of such a sum just amounts to the not very profound repeating of the question back again. So this is a serious contamination, I think, of rational number arithmetic. Can you imagine a situation where undergraduates, if they're answering questions in a test, raise their hands and say, "Excuse me, sir, are we working over the rational numbers or over the real numbers on this test?" And they're hoping that their instructor says, "Oh, we're working over the real numbers." Great! We're working over the real numbers, anything goes. You have an infinite sum? That's what it is. You have a finite sum? That's what it is. You have a computation like this? Just repeat the answer back. Real number arithmetic is just so simple to do, isn't it? Okay, so it's a lot of reasons, okay, to be highly skeptical of this standard story for real numbers. Real numbers as equivalence classes of Cauchy sequences of rational numbers. It doesn't work. We are also going to look at the last sort of serious bastion of real number arithmetic, which is the idea of Dedekind cuts. But before we do that, I want to have a short diversion to actually looking and opening up some classical calculus texts and real analysis texts to see what they do in terms of addressing this issue of how we set up the real numbers. Okay. It's got to be more than just a discussion, a debate with me on one side and many other people on the other side saying, yes, it is, no, it isn't, yes, it is, no, it isn't. It's sensible to also look at the literature, look at the evidence, look what's actually written and see, does what these people do make sense? Can we open up a book and find out what real numbers are? How do we do arithmetic with them? How we prove the laws of arithmetic? So I'm going to have a look at a selection of interesting texts, which will, if nothing else, introduce you to some fine books. But I hope it will also open your eyes to the almost universal weaknesses that this real number theory really comes with out there in the educational world. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.